Hi everybody. So today's a really exciting day because I'm happy to announce that here at Flamethrower AI we're going to be launching a new instruction series. And this series is going to be called Flamethrower Interview. And we've already got the course up online on our website. If you go to this URL, I'll put it down in the description, but if you go to that URL, you can see the syllabus of the courses or the lessons that we've created in this course. So basically what our goal here is to create a really comprehensive data bank of machine learning interview questions, something similar to like what you have with LeetCode for regular software engineering questions, but this in particular geared towards the machine learning interview, because there are a lot of, like I said, software engineering interview questions for like that generic position, but really quite a bit fewer when you drill down into the machine learning interview. And really machine learning is so broad that I haven't really found a good centralized data bank of questions yet. So that's the goal of this course, and it's completely free. You can go to our website and sign up. And this is just a sampling of the lessons that we're going to have. We're adding new ones all the time, so that's something to keep in mind. And like I said, this course is totally free. Just go to the link in the description and sign up. Now let's go and dive into some questions. So in this video, we're going to be focusing on questions that might come up in the interview about regularization. And regularization is this interesting topic in the context of the ML interview, because what I've usually found is that the topic of regularization comes up usually within some broader context. So it's more rare, I think, that somebody will ask you a question about regularization directly, but what they might do is they might ask you a question about, what sort of model would you create given this data set and the task that you're trying to accomplish? Or compare and contrast the advantages and disadvantages of different models. Okay, and now given that you've selected this particular model to use on this problem, well, let's look into tweaking it. So what sort of regularization can you add to that model? And that's what we're going to talk about in this video. And these are some kind of generic regularization questions you might come across. And maybe with future videos, we'll do some more in-depth ones and focus solely on a single question for a single video. But let's just run through these. So let's look at the first one. Does L1 or L2 regularization produce models with sparser weights? So that's a very, very common type of question you'll get asked on regularization, and you should know the answer to that and be able to explain why. So let me just sketch out why. And basically the answer is that L1 regularization produces sparser weights. And why is that? Well, if you draw out the contours of the weights in weight space, so this might be the first component of the weights and the second component of the weights, and we're simplifying here and just assuming a two-dimensional weight space. But this is basically what the contours look like for, this is L1 regularization. And this is a common diagram you'll see drawn in many like intro ML classes. Likewise, let's look at the diagram for L2 regularization. So in L2 regularization, you have these concentric circles. Okay, and then basically the thing that's usually proposed is that you have some optimization algorithm or some loss surface where you're searching for the optimal solution to your problem. And let me undo this. That was a bad take. But basically the idea here is you have some solution out here or some loss surface here. And the optimal solution determined by your optimization algorithm is going to be where these two contours intersect. And it turns out that with L1 regularization, there's a tendency to intersect on or close to these corners in the weight space contour. So that creates very sparse solutions because you have a high activation value here on W2, like let's say it's 1, but then the corresponding W1 value is 0. So that's a very sparse weight matrix or weight vector. Now conversely, with L2 regularization, you're more likely to have it intersect somewhere in the middle where you sort of get this even distribution between W2 and W1 in your weight vector. So you get something maybe like 0.5, 0.5, somewhere along those lines. So as you can see, this is much more diffuse. So that in a nutshell is why L1 gives you sparser weight vectors when you use L1 regularization on a problem. And actually, L1 is so good at giving you these sparse weight vectors that it's actually commonly used as like a method of feature selection. Because if you have like 0 in this W1 component here, well, you're effectively not using that component, so you could basically just get rid of that feature. So that's one way to think of it. Okay, let's go on to the next problem. What's another term for L2 regularization? That would be weight decay, I believe. Yeah, so weight decay is one term that's commonly used, or Tikhonov regularization. That's more in the statistics literature, but that term is also used. So if they refer to L2 regularization by one of those terms, now you know what they are, so you won't get tripped up. What is elastic net regularization? Okay, so elastic net regularization is simply, it just combines the benefits of L1 and L2 regularization. So I'll just write EN for elastic net. So it's some combination of lambda 1 times L1 regularization. So this is the 1 norm of your weight vector plus lambda 2 times W2, that's the 2 norm. Oh, that's not W2, sorry, it's still W. But it's the 2 norm. And you might have some condition like lambda 1 plus lambda 2 is equal to 1 to make this like a convex combination of sorts. But yeah, basically it's just that. It's a linear combination of L1 regularization and L2 regularization. So it's useful in some cases because you kind of get the best of both worlds in some sense. So this is your penalty term, omega, that you add on to your loss function. Okay. What does regularization help prevent? That's pretty simple. Regularization primarily is used to prevent overfitting to the training set. Is dropout a form of regularization? Yes, so dropout is very much a form of regularization. And how you can think of that is let me draw out the picture. In dropout, you've got a neural network, right? Yeah, something like that. They're all interconnected in some way. These circles are the neurons, and these lines are their connections. And basically with dropout, you just randomly zero out each neuron with some probability p. So maybe you use p equals 0.9, so you zero them out with a 90% probability, or so this would be very high regularization because you're using very few of these neurons in each pass. Or you could use something like p equals 0.2. Then you'd only be zeroing out 20% during each training pass. But on each training pass, you zero out a different set of neurons, a different 20%, say, or 90%, depending on what your p-value is. And based on that, you're effectively training a slightly different model with different neurons on each pass. So this can actually be thought of as a form of model averaging, which is regularization. Another way to think of it is just as follows. Basically, when you zero out some of these neurons, you're constraining like the effective dimensionality of the weights. It's like sort of performing L1 regularization in reverse in a way. So when you do L1 regularization, you get these sparse features, these sparse weight vectors. So some of these neurons, if you will, are effectively driven towards zero after you perform the regularization. In dropout, you're just choosing in advance which ones are going to be driven towards zero, and then training the model with the remaining weights. So you're operating with a constrained number of weights, and that provides that regularization effect. Okay, this is one I like. This is definitely something I could see coming up in an interview as maybe like an add-on to a question about neural networks, or just its own question. But it says, if someone handed you a neural network to train but didn't let you alter it, how would you regularize it? So the simplest way to do that would just be to use what's called early stopping. And in early stopping, let me draw another thing out. So in early stopping, you have, this is like your training error, and this is your, I'll use a different color for it. The green line is your test or validation error. So generally, when you're training your model at the beginning, the training error and the test error will go down simultaneously. After some point, however, the test error starts to level off, whereas the training error will keep going down because you have access to all that data and you can learn it arbitrarily in many senses. And then after some point, you can actually start to overtrain, and this is when overfitting happens, and the test set or validation set error will actually start to increase again. So early stopping means you just cut off training at some point, some early point before this starts to happen. So you can cut off training here per se, and that should give you, optimal error, hopefully, if you do it at the right point. And it prevents this overfitting at the end, so it's a form of regularization. We've only got 2 questions left here. What's the term for regression with L2 regularization? That is called ridge regression. Simple enough. And what's the term for regularization, or for regression with L1 regularization? That is called lasso regression. So another nice term to keep handy. Okay, so that just about covers some, I say relatively easy regularization questions. In future videos, we might go into some more advanced ones, but hopefully that gives you a good start in prepping for the machine learning interview. And if you understand and master all these questions, you can check out the resources on our flamethrower.ai website. We've got a great course on deep learning and other resources on there that you can use. So that's a really good way to practice. And in a future video, we'll do some more advanced questions. But even just mastering these, you'll be well ahead of the game in terms of preparing for your machine learning interviews as far as these questions are concerned. So I hope that was helpful, and I'll see you for the next one.